Greetings, ladies and gentlemen, and welcome to our Big Ideas Lesson 7.4, page 310 for you 8 general students, and lesson 14.4, page 648 for the 7th accelerated students. We're continuing on our real numbers and Pythagorean theorem, where today we're going to apply what we learned to approximate some square roots to the nearest whole number and the nearest tenth. Our essential question: how can you find decimal approximations of square roots that are not rational? So I guess you can figure it out. We're going to be taking and square roots of and approximating them for irrational numbers because they're not rational. Ladies and gentlemen, I know you're a person of character. You went to the top of page 310 or 648. You read all about those terminating and repeating decimals. You read about the perfect squares and the perfect cubes and the non-perfect squares and the non-perfect cubes, and you know where they go in the real number system. Real quickly, going to remind you, the real number system made up of rational and irrational numbers. Let's talk about our rational numbers first. We have the smallest set of rational numbers, which we call our natural numbers, or we sometimes call them the counting numbers. And those are 1, 2, 3, ... forever and ever and ever in that direction. We then have the next biggest set, which we call the whole numbers. No, let me get out my other color here. Whole numbers. And all we did with the whole numbers is added 0 to our natural counting numbers. So it starts at 0 and goes 1, 2, 3, and it goes forever in that direction. And then we have our next biggest set. This is the set we started out the year with. For our accelerated students and the 8th graders, it was your first unit in 7th grade, was integers. And the integers took the whole numbers and they added the opposites. So the negative numbers. So I'm just going to write -3, -2, -1, then we go to 0, and then we get to the positives, 1, 2, 3. And of course it goes infinitely in both directions. And then we have the largest set of rational numbers, which we just call rational numbers. Why? That's because what we do. Our rational numbers can be written in the form of A over B, where B is not 0, right? And what would happen is that would give us a number that is not an integer. In fact, it would give us a decimal. So we have fractions that if we ever do the math with the fractions, because remember that fraction bar does mean division, numerator divided by the denominator. They all can be written as fractions and or decimals. And when you write them as fractions, you do the math, you will get a decimal. And those decimals in our rational number system either repeat or terminate. I should have talked about terminating first. Because if it terminates, it's rational. It could not terminate. It could go on and on and on forever and still be rational because it repeats. So either one of those would cause the number to be a rational number. Let me give you an example of both kinds. If I have 1/4. 1/4 is written in the form of A over B, and when I do the math, 1 divided by 4, I get 0.25. That is a terminating decimal. So it is rational. Now let's talk about, how about 1/9? 1/9 is as a decimal 0.1 repeating. It does not terminate. It does not terminate. However, it does repeat 1 every single time. That means it is a rational number. All right. So we talked about our rational numbers. And this is all part of the real number system. And so we then have our irrational numbers. And you read about it. We're talking about square root of non-perfect squares. I'll extend that all the way across. So for example, square root of 13, square root of 94. These are non-perfect squares. If you did the math, they would give you a decimal. That decimal would not terminate and it would not repeat. Both. It never terminates, it never repeats. You can also write them as A over B that do never terminate and never repeat. Our most famous one, 22/7, which we call pi. And you know pi, 3.14159, and it goes on and on. It never terminates, it never repeats. We could also have cube roots of non-perfect cubes. You can take a fourth root of a number that's not a perfect number multiplied by itself 4 times, etc., etc., etc. Of course, I gave you this example of the irrational and rational numbers within the real number system, so you have that for a backup. Ladies and gentlemen, the first part of what we're going to do today is say, okay, let's identify these numbers from the real number system as either rational or irrational by classifying them. And of course, if they are whole numbers or counting numbers or integers, we're going to identify all of that. So we're going to classify each real number. We know they're real, so we don't have to go any further than that. So we're taking a look at this first example, 0.12122122221, and we got to decide, does it terminate? And the answer to that question is no, because we can see the ellipsis at the end. It does not terminate. So now we have to look at whether it is repeating or not. If it repeats, it's rational. If it does not repeat, it's irrational. And in fact, it does not repeat. So this is an irrational number. Going to the next one. We have the negative square root of 196. And of course, doing the math, the square root of 196 is 14. Bring down the negative. So this is an integer, and it is rational. Of course, it's also real. The cube root of a negative 1,728, probably going to need to use your calculator for that. And you know that a negative times a negative times a negative, we can do that. It would give us a negative. So you can have the cube root of a negative number. You can have an odd root of negative numbers. You cannot have an even root of negative numbers. Doesn't work. I mean, it does. You'll learn about that later. Those are imaginary numbers. Anyhow, the answer to this one, 1,728, does happen to be 12 cubed. And so this negative 12, of course, it is also an integer. And it is rational. And of course, it is a real number. The square root of 27, non-perfect square, irrational. You should know all your perfect squares. 81 over 3, well, that gives us 27, which is a terminating decimal, 0.0. It terminates, it does not repeat. It is a counting number, a natural number. It's an integer. Oh, excuse me, I left one out. It's a whole number. It's a integer, and it's rational. Of course, it's also real if it's all those. Negative 0.47 repeating. It has the bar over there, so it is a decimal that does repeat. So this is simply rational. All righty, ladies and gentlemen, here's our first quick write of the night. Please write these numbers down, complete that, take a quick break, come back and see me for our second and last video of the night.